Hi guys, welcome to Learn Electronics Repair. This is the amplifier we were looking at, the Yamaha PC2002M, and it has a protection fault on both channels. In the first part of the video we used the schematics and we found out where the problem is, which is in this amplifier module. So this is part 2. We're going to use the schematics again to see if we can determine where the fault is likely to be on this module before we dismantle it. But first, let's have a quick resume of how we got to this point. And a few subscribers were saying they couldn't follow the schematic very well with my mouse pointer, so let's see if we can do a little bit better today. And here is the part I was interested in first. So this is the block diagram. It shows one channel of the stereo amplifier. It basically says that channel B is the same as channel A. So these two channels are identical. And we can see we have the inputs coming through an operational amplifier type circuit and a differential amplifier. And that produces the signals going into the output stages. These are the output stages, and this is where the speaker connects. Here. This then is the junction between the NPN and PNP transistors that make up the output stage. This point also feeds back into the differential amplifier. This is the feedback circuit. So you have the signal coming in. This is a constant current source, this little symbol here. We have a proportion of the output signal coming back, and it's effectively between the values of the resistor here and the resistors here. This sets the gain of the amplifier. Now the problem we have is that the protect lights are on both channels. And I commented that it would seem that if we have protection on both channels, either both channels of the amplifier have effectively the same type of fault, or we have a fault somewhere in something that is common to both amplifiers. And the first thing that came to mind was the power supply rails. Maybe we have a problem with the power supply rail. So the next thing I did, and I'll explain again, I looked at the way the protection circuit works. It shows it on the block diagram. So I'm sure you can see we have an input to this circuit coming from, if you like, the output of the amplifier. We have a relay, and the relay has to close to connect the speaker to the output of the amplifier. So this is detecting something on here and deciding to switch the relay on if it's happy with what it finds, connecting the speaker. We also have a little driver here to the protection LED, which is down here. So that's basically how the circuit operates. The other thing we can see here is the power supply rails. So we have a plus and minus 80, we have a plus and minus 15, we have a plus 12, and it says these are regulated power supplies. And then we have two more power supplies, plus minus B, plus and minus BA. So the next stage we took to look a bit further was to have a look at the protection circuit in more detail. Here then is the amplifier and the protection circuit. This is, it says relay driver, this is the protect circuit, and this is the amplifier. If we just look, we have coming in here on these colored wires, orange and red. We have signals coming from here, orange, red. So this is the input circuitry of the amplifier, the preamplifier if you like. And coming out of here is effectively the positive half cycles of the audio waveform driving this half of the amplifier, the NPN transistor half, and the negative half cycles of the waveform driving these transistors, the PNP side of the amplifier. So basically this circuit handles all the positive going parts of the audio signal, and as it crosses zero, this half handles the negative half, if you like, of the audio. If you want to think of it another way, you could say that these transistors are pushing the speaker cone, with no signal, it comes back to the middle, and then these ones are pulling it the other way. That's how it moves the speaker and how we hear the sound. What the protection circuit basically does on this amplifier, it monitors the voltage here. So this is the junction between all the NPN and the PNP transistors. When there's no audio, or when the waveform of the audio passes is 0, the voltage on here will be 0, the speaker cone in its rest position, the middle position. Now, a common problem with an amplifier is you have a fault in here, maybe a short circuit transistor or something wrong with the drive signal, and these transistors turn on. If that happens, you will have a DC voltage here, and that's called a DC offset. And the same on this side. If you have a problem on this side, you can have some sort of fault in here that produces a negative voltage here, a negative DC offset. Both of these things are very bad things. You do not want a DC voltage going into your speaker, because your speaker is an inductor, it's a coil. When there's AC feeding into it, the speaker cone is moving and the inductor has inductance. So at audio frequencies, when this is driving music, the speaker has a higher resistance than it does with DC. With DC, it's just 4 ohms. And if you're connecting from here, 80 volts into that speaker at 4 ohms, you're going to get 20 amps going in there. You will burn out the speaker. You may well damage the amplifier further, but whatever happens, you can guarantee it's going to be something bad. So we monitor the voltage here, this side of the relay, and you can see the signal comes down here, along here, and through these 2 resistors. This end of the resistor network is ground. If you look, we have 120k from the signal, the audio waveform, and any DC offset, 120k into this IC, and we have 33k to ground. So roughly speaking, 120 to 30, this resistor is 4 times bigger than that one. So 4/5 of the output voltage will appear across this resistor and 1/5 across here. This signal now comes through a 100k resistor, a couple of capacitors here, which you can see are 10 microfarad 25 volts into this chip. This looks like an operational amplifier, but it's not exactly that. I'll explain why in a moment. The other input to this pseudo operational amplifier is connected to ground. And we can see in an idle situation, this voltage should be 0 here. It will turn this on. The output here will go down to ground, and that will switch the relay on. The reason it switches the relay on when this goes down is because the other end of the relay is connected to push 12. So there's 12 volts permanently on this end of the relay. If you have 12 volts on the other end, there's no voltage across the relay, it's switched off. If this chip pulls this point here down to ground, there's 12 volts across the relay, it switches on. And that drives our contacts and connects the speaker. We also have this transistor. Now, when there is 12 volts on here, so the relay is switched off, we are in protection mode. That 12 volts also puts a voltage on the base of this transistor via this resistor. And if you look at the emitter of this transistor, it's not connected directly to ground. It's connected via 2 diodes. When the transistor is conducting, you will have a voltage drop across the 2 diodes of about 0.5 volts each, 0.55, something like that. So the emitter will be at about 1.1 volts, somewhere in that region. Okay. The collector, because the transistor is turned on, voltage on the base, is also at about that 1.2 volts or thereabouts, 1.1 volts. And that connects to the protection LED. It actually connects the cathode of the LED to ground, basically, via these resistors. The other end, the anode, is fed from 12 volts via resistor, so the LED turns on. We're in protect mode. When this chip switches the relay on, so we're not in protect mode, there's now 0 volts here. It's below the voltage of the emitter. This transistor turns off, And we now effectively have 12 volts on here, the same as the other end of the LED, so the LED is off. That's how it works. I did say it's a little bit more complicated than just an op amp. And the reasons are twofold. One, the DC offset, if there is a DC offset here, could be positive or negative. So we also want this to switch the relay off if there's a negative voltage on here as well as a positive. That's why it's not just an op amp. You can also tell that the voltage here can be positive or negative. If you look at these capacitors, these are electrolytics, but they're bipolar, BP. There's no plus sign by them, yeah? If you look at some other ones, look, there's one with a plus sign, okay? It doesn't say BP. So the voltage on here can be positive or negative. This chip detects there is a voltage regardless of the polarity, which an op amp won't itself quite do, and it switches the relay accordingly. Another thing, when the amplifier is running, on here is the actual AC waveform, the audio waveform, going positive and negative all the time. It doesn't keep switching the relay on and off. It knows the difference between an AC signal and a DC offset. I don't know what this chip is. Maybe we can have a look later on when we take the amplifier module apart, but that's what the chip is doing. So it's a special chip, I would say, for the protection circuit. Because we have a protection on both amplifier channels, my first thoughts were, as I mentioned before, power rail problem. So the next thing I looked at was the regulated power supply. This is the power supply. Now let's have a look at this in a little bit more detail. We have the transformer here, and you see we have quite a few windings on this transformer, okay? So this power supply, this is generating B plus and B minus, these voltages. We have a large bridge rectifier going to some large capacitors, 22,000 microfarad, 100 volts, a pair of them, one on the positive rail, one on the negative rail, and this is giving us 87 volts plus and minus. That's the first thing I measured. I have that. We have another voltage rail here. This one is plus and minus BA or B alpha. Now, when I looked at this on the first video, I said, oh, there are 16 volt capacitors here, so this voltage rail must be something less than 16. But I was wrong, and the reason I was wrong is quite evident if you look where the capacitors are connected. So this one, the positive end goes to B alpha, and the negative end goes to the positive end of the capacitor on B plus. So this end of the capacitor already has 87 volts on it. This end must be higher. It's polarized, it's positive, it can't be less. It must be higher than 87 volts on here. And the same with the other one. You see the negative of the 16 volts, the positive end goes to here, again on the 22,000. So you have to think upside down or backwards, but the reverse applies. Minus B alpha must be a lower voltage than minus B. The reason they've done this, I'm sure, is so you don't have to have some more big 100 volt capacitors. Effectively, they are just putting this one between the 87 and there's something a bit more, well, less than 16 volts more, we can say for sure, and between the minus 87 and something less than 16 volts more negative, okay? I think that's just to make smaller components, basically, less space. What else do we have? Well, we have plus minus 12 volt regulated power supply. But if you look at this thick wire, this is ground. Okay, this is ground. Here's your main smoothing capacitor from ground to here, 25 volts. This is the voltage regulator. This is called an emitter follower circuit. So we have some voltage coming in here, 16. We have 12 volts on the base, and the emitter is 11.6, a little bit lower. Remember, there's always 0.4, 0.5, 0.6 volts across the base emitter junction. That's how an emitter follower works. It follows the voltage on the base, basically. These are actually both emitter followers, and that Zener diode there on the base is setting the voltage reference 12.5. These are interesting circuits, and we have another one up here which is basically the same sort of thing but more complicated. So I'm going to make another video just about how this works. It's very interesting, and it's something you really should understand if you're doing repair work, especially on this sort of equipment. Back to this anyway, so you can see this is just a plus 12 volt supply, it's not minus. There is no negative 12. You can see from this. We then have another winding, center tapped. This is earth or ground. This is plus 15 and minus 15. This uses two voltage regulators, which it shows here, 7815, 7915, typical 1.5 amp positive and negative voltage regulators. And then we have this circuit. This is the plus and minus 80. Now this one is where I found the problem. So I won't go exactly into this one yet. I want to do a video about this type of thing, coming probably this week. But what I found is that the plus 80 is missing. I don't have a plus 80. There's two red wires. One goes to one amplifier, one goes to the other. The same with the two blue. The minus 80 is there. The plus 80 isn't. I then took this module out. I checked all the transistors, all the diodes. I looked for shorts. I couldn't see anything wrong. So I thought probably the fault is somewhere else. And the next thing I did was to measure the resistance on the two red wires. One is very high and the other one was 75 ohms or something like that. A bit less than 80. And that's what was causing the problem. Once I disconnected that on one amplifier module, the protection came off on both. But one of the amplifiers is missing its voltage supply, so one channel would work, one wouldn't work, but there was no protection anymore. What I found then wasn't a short. It was 75 ohms, almost 80 ohms to ground on one side, one channel. Now, you may think 80 ohms isn't anything like a short. I mean, 80 ohms is a fair bit of resistance, yeah? And you are right, but what you also need to consider is the voltage on this rail. If this was a 10 volt supply, 80 ohms, you'd have an eighth, about 125 milliamps flowing into that short, which isn't a short. But with a plus 80 volt rail, 80 ohms or a bit less, you've got 1 amp or a bit more. So you're now drawing an amp from here. Now, even an amp, 1 amp, might not sound that much. But at 80 volts, 1 amp, well, wattage, watts is volts times amps. So that's 80 times 1 is 80 watts. Yeah, so that's a lot of power. So basically, one of two things is going to happen. Either A, whatever is the 80 ohms here is going to burn up because it can't handle 80 watts. Or two, this power supply is going to shut down because it can't supply 1 amp. In our case, the power supply is shutting down. There's no plus 80 on either amplifiers, and this is why we have the protect mode. What do all these voltages do? Well, let's have a look at this amplifier, the power stage. So basically, all the main output transistors, the collectors of the NPN, that's this rail. Okay, this rail. And this rail. Okay. This is the plus or minus 84 I measured. It's a bit higher, in fact, when I measured it. It was more like plus or minus 87, but that is that rail. That is B plus and B minus. Now, I mentioned B plus alpha and B minus or B negative alpha must be a bit higher. We looked how the capacitors were, and in fact we can see they are minus 90 and they are plus 90, and they drive this transistor. This is the driver for the output. Okay, the regulated 80 volts minus and plus, they drive the pre-driver stage. So we have basically an 80 volt supply around here, a 90 around here, and an 84 around here. One other thing I find very interesting about this amplifier, and so interesting I'm going to mention it. The driver is driving the 4 output transistors, and then we have resistors from the emitters to ground, and the same thing on the negative half of the amplifier. Okay, but look, we have a voltage here, 0.55 of a volt through the base resistor onto this transistor. So this here has about 0.55 of a volt on. That's just switched on. So as soon as we start getting any audio waveform, the transistor turns more on. The reason they do this is you call it base bias, and that's because you want the transistor to start conduction as soon as the audio waveform goes above 0. You don't want it to go up to half a volt to switch the thing on first. Otherwise, you'd lose a chunk out of the middle of the sine wave when it's near to 0. So that's 0.55. Then look, we have a resistor, 0.33 and 3.3, different values. And this has 0.53, so this transistor is not as turned on as that one. And the same with this one. Through another resistor, a different value again. And then the last one through another resistor, so that's all of these in series, less voltage again. So what that means is, when you start getting an audio waveform here, as the AC comes above 0, this will switch on straight away. So first of all, just this transistor is driving the speaker. 0.2 volts higher, this one comes on. So we now have 2 transistors driving the speaker, and you can see just after that, 0.52, this one comes on, and then sometime later, quite a while later, another 0.7 volts on the drive, this one comes on. So effectively, as the AC waveform goes up, we're switching more and more transistors on. When we reach so far up there, they're all on, and they all stay on until the voltage comes back down towards 0 again. And as it comes back down, these effectively switch off and turn. Same, of course, on the negative half. I've not seen this before. I wouldn't say it's rare. It's just an interesting design. I've not seen this. In our case, the power supply is shutting down. There's no plus 80 on either amplifiers, and this is why we have the protect mode. What else do we have in this schematic? There was one other thing. I showed it in the previous video. It gives us a list of all the coloured wires and the abbreviations. And on the schematic, very nice. And they've put all the colours. So it was easy to work out which wire went where, which is how I managed to figure out where the plus 80 was on the 2 red wires. What do all these voltages do? Well, let's have a look at this amplifier, the power stage. So basically, all the main output transistors, the collectors of the NPN, that's this rail, okay, this rail, and this rail, okay. This is the plus or minus 84, which I measured. It's a bit higher, in fact, when I measured it. It was more like plus or minus 87, but that is that rail. That is B plus and B minus. Now I mentioned B plus alpha and B minus or B negative alpha must be a bit higher. We looked how the capacitors were, and in fact we can see they are minus 90 and they are plus 90. And they drive this transistor. This is the driver for the output, okay? The regulated 80 volts, minus and plus, they drive the pre-driver stage. So we have basically an 80 volt supply around here, a 90 around here, and an 84 around here. One other thing I find very interesting about this amplifier, and so interesting I'm going to mention it. The driver is driving the 4 output transistors, and then we have resistors from the emitters to ground, and the same thing on the negative half of the amplifier, okay. But look, We have a voltage here, 0.55 of a volt through the base resistor onto this transistor. So this here has about 0.55 of a volt on. That's just switched on. So as soon as we start getting the audio waveform, the transistor turns more on. The reason they do this is you call it base bias, and that's because you want the transistor to start conduction as soon as the audio waveform goes above 0. You don't want it to go up to half a volt to switch the thing on first. Otherwise, you'd lose a chunk out of the middle of the sine wave when it's near to 0. So that's 0.55. Then look, we have a resistor, 0.33 and 3.3, different values. And this has 0.53, so this transistor is not as turned on as that one. And the same with this one. Through another resistor, a different value again. And then the last one through another resistor, so that's all of these in series, less voltage again. So what that means is, when you start getting an audio waveform here, as the AC comes above 0, this will switch on straight away. So first of all, just this transistor is driving the speaker. 0.2 volts higher, this one comes on. So we now have 2 transistors driving the speaker, and you can see just after that, 0.52, this one comes on, and then sometime later, quite a while later, another 0.7 volts on the drive, this one comes on. So effectively, as the AC waveform goes up, we're switching more and more transistors on. When we reach so far up there, they're all on, and they all stay on until the voltage comes back down towards 0 again. And as it comes back down, these effectively switch off and turn. Same, of course, on the negative half. I've not seen this before. I wouldn't say it's rare. It's just an interesting design. I've not seen this. My gut feeling, and I am not an audio engineer, I'm a fixer, a general purpose electronics fixer. But my gut feeling about it is so that you reduce the quiescent current when the waveform is near or at 0. Because all these transistors, partially or just slightly turned on when there's no drive waveform, will give a certain amount of current all the time into the output. And they are cumulative, so the more transistors you have, the more quiescent current you have. But in this thing, it looks like when the waveform is at or near 0, only the first pair of transistors is working. I know a lot of you guys know a lot more than me about this sort of thing. Has that circuit got a name? And tell me I'm right about why I say it was done that way. Now to the fault. Can we trace where this is likely to be before I take the rest of the amplifier apart? This is where we have the problem, the red wire going to one of the channels, plus 80. That, if you look, comes in here, red. It goes via a 2.2 ohm resistor and it comes back out on yellow. That's one of 2 places it goes. The one on yellow then comes into this part of the circuit, so we have a transistor. We have 2 diodes, we have a resistor. I think, yeah, these are fusible resistors. We have 390 ohms. We have another transistor to negative. So the first thing I'd say about this, there's no obvious path to ground here, at least. This doesn't connect to ground, and the short is to ground, or the low resistance is to ground. So I don't see how that part of the circuit could be causing it. If we had a short circuit base emitter here, well, we have, is that a 100 ohm or is that a 56 ohm? And we have a 0.33 and a 0.33 and another 120 ohm, and again this doesn't go to ground. So I don't see any obvious path in here to cause a short, or rather 75-80 ohms between there and ground. But we should be able to figure this out by disconnecting this yellow wire if we can. If we disconnect the yellow wire, if the fault is still there, the problem is over here. If the fault isn't there, the problem was over there. But let's have a look at this side. This is where I think it might be. But remember guys, there's a lot of supposition until we prove it, okay? So in here, well, There's a 2.7k, so the problem can't be going down that way. 470, 470, 5.6. So I don't see any path down here of like 75 ohms. There's resistors in the way. Yeah, you can't be a short here because a high value resistor. And we will see the high value resistor. So at the moment, I'm not exactly certain where the problem is. I don't see anything obvious. We could have a faulty capacitor. I mean, there's a capacitor there that goes to ground. This heavy track is ground, so maybe a faulty capacitor would do it. In fact, I'm sure that would do it. The front part of this appears to be missing, but this voltage rail only goes as far as here. So yeah, maybe a bad capacitor there. What else would cause it? Well, as I say, all these paths I can see all go through a higher value resistor. If we had a short circuit diode, the next thing we've got is 470 ohm resistor, so it can't be down that route. Can you see what I'm doing? I'm trying to find obvious routes where the low resistance is. I can see that. Do I see any in here? Well, you can't go this way because there's diode, a very funny looking diode, but there's also a 390 ohm resistor, so it can't be going that way, even if that then could have a shorted transistor and come back to ground. There's no route there. Okay, so let's figure out where these red and yellow wires go, and let's see if we can figure out a bit more where our problem is. So here's our red wire, 79 ohms. Yeah, it wasn't 75. That looks like the yellow wire coming off this connector, and that goes to here, so it should still be here. 77 ohms. This is lower than that. And if you noticed on the schematic, and I'm going to show you again what that means. It means the resistance on the yellow to ground is lower than on the red, and look what's in between, a 2.2 ohm resistor. So the fault is here somewhere, but unfortunately we don't know which side because the yellow wire and these all power from this point. Let's disconnect the yellow wire. So that goes to a little plug down here. I should be able to get to it. There it is. Right, where's the short? Well, let's look on the red one again. Is it gone? No, it hasn't gone. So the fault is on this board. The fault is on here. If we go to the yellow wire now, it's 60 meg. So fault is definitely on this board, okay? Now let's take the thing apart. Okay, I have the module sort of dropped to one side. I can't easily remove it at the moment. But what I can do is take this PCB off. We know where the problem is basically, so it makes it easier just to get this board off. And hopefully we'll find this without having to power this up. It's quite difficult to show you this, guys. You can see the PCB here. I'm using the side mounted camera. Moved a little bit further away. Okay. So this is where the 80 volts comes in. And we can see we have the 80 ohm resistance. Now I've disconnected this one. This basically goes down to the main amplifier board. I've disconnected another one there, which disappears somewhere down there. And the low resistance is still there. Okay, but when I disconnect this one, it's hard for me to show you, but it's like an audio cable, red, white, ground, okay? So when I disconnect that one, it goes away. Yeah. It's not there anymore. So wherever this is going, this appears to have the problem. I'm going to have to get somewhere where it can work a bit better. But anyway, that low resistance is somewhere on that cable. I've put this back on pretty much now. It's held on with one bolt, but it's there. So I've disconnected that wire. Let's see what we have. Well, we have like 10 kilo ohms or more. Okay, so the short has gone. Well, low resistance has gone. So that high voltage must come down this connector. Let's have a look. We'll go from the red wire here to here. Yeah, it reads 82 ohms to there. Oh, that isn't right. Because that is a ground connection. Look on the other channel. Looks like I was wrong again, but right, that's how it goes. So we go from the red wire here. 10k or so. 9k or so, 10k or so. Look on the other channel. Okay, from the red wire here, $80 ohms to here. That just happens to be the ground connection on this. You can see like the screened wire. So effectively this is just connecting that point to ground, which is why when I disconnect this, the resistance goes away, but the low resistance is still on this board, 80 ohms from here to here. That's just the path from there to ground. Okay, back on this one again. Here's the board. I've taken it off the amplifier. Here is the 80 volts plus, and this is the ground connection on here, and there is the 83 ohms I'm actually reading now. Slightly less the other side of that resistor. That's the 2.2 ohm resistor. So the problem is on here somewhere. Let's see if we can find it. Well, as I noted before, from this point here, there are no obvious paths to ground apart from this one, which goes to ground here. So that's the only really obvious one I can see. If we look at the same components on the layout, so we can see here, this is where the power was coming in, that's the yellow light going back out. We have these two components. Again, we can look around this track, put anything like, for example, a shorted diode there, wouldn't have a path to ground. It is this one. This is ground. So both of these components basically connect via this wire J to the end of this connector. This is when I disconnected, the short to ground went away, but I still had 80 ohms to here. So if I lift that wire and we no longer see the 80 ohms to the ground pin, the problem is over here somewhere. Let's have a look. This looks like it might be the problem actually. You see this horrible glue stuff here? I wonder if that's gone conductive. That's the diode, that's the capacitor. This is J, so we can lift J. I mean, we have a similar thing here, but it's not quite as dark as that one. But if that's caused a problem, this probably will as well, unless I remove that. Let's lift this one. The wire's lifted out of the board now. So if we go from the input to here, we have about 90 ohms, okay, and obviously there's no connection to there anymore, so the problem does appear to be here. We can see it across the diode. I'll take the capacitor out. Okay, let's just take this out. It could be the capacitor, could be the diode, but I'm a bit less suspicious of that. Okay, capacitor's out. What have we got now across the diode? Well, it's gone up, but it's still fairly low. Let me get rid of this crap. We'll try a plastic spudger. I've removed some of it. Let's have a look. So what we get across the diode. There you go. Mega ohms. So that, guys, was the cause of the problem. That stuff, yeah. Look at the capacitor we took out. Mega ohms, okay. So that's what it is. That glue. Okay. There's more of it around these capacitors. Another one down there. Obviously we'll have the same on the other module as well. So there's going to be a bit more time I need to spend to actually complete this repair. But we do know that when we disconnect the cables to this one, the protect lights went off on both. So I'm happy to go away in my own time and do that now. I think I've shown you guys the most interesting thing. I don't believe any of you doubt for 1 minute I've actually fixed this. I just need to spend a couple of hours really now and remove all the rest of this stuff from the other boards as well. See if I can find it anywhere else, because obviously if it causes a problem here, it's going to cause a problem elsewhere. I hope you guys enjoyed that. Actually, a bit of a detective story. I didn't actually expect that to be the problem, to be quite honest. But I hope you can see how we can use a schematic to find a fault like that. Even before I actually found the cause of it, we'd been through those schematics, we'd narrowed the problem down to where it was on this board, and we'd even narrowed it down using the schematic and looking for paths to ground. We'd said the only place the problem can be, in all honesty, is there. And what did we find? Yeah. So that's how schematics are used as part of your repair work. And I hope you guys now can do the same. Much easier than you could before. You'd probably say, without the schematic, we probably would never have found that. I wouldn't have found that fault, I don't think, without the schematic. If I had have done, it would have been really time consuming. I would possibly have figured out the 80 volt rail was missing, the regulated one, but it would have took a lot of time. I may have decided somewhere along the way as I wasn't going to find that one. But yeah, it's done. Okay, I'm looking forward to seeing you all soon on another Learning Electronics Repair video. I suspect the comments section on this one, down there, will get very long. So get typing, guys, and ciao for now from Learning Electronics Repair.